Hi, Terry here, and welcome back to Times Gone Tech. And don't bother asking me what my pronouns are, because that is the absolute stupidest question anybody could ever think of to ask. All right. And in fact, anybody who brags about the pronouns is even stupider than the person asking about it. You can call me anything you want because I've probably already been called it. Just don't call me late for supper. Hey, okay. Having said that and gotten your attention, I want to do a quick follow up on my introduction video and the final video of the Magna Gonne V1. Yeah, I want to talk a little bit more about that. I got a lot of views on it, got some good comments and some good suggestions. A couple of those suggestions I'm actually going to follow up on in some future videos. There were some pretty good ideas there, but I kind of already have a plan that I want to go through first. Yeah, there will be a Magna Gonne V2. In fact, it's already in the design stage and parts are already being ordered. A couple of weeks, 2-3 weeks maybe, and we should be ready to bring it back out. It might explode even more spectacularly than V1, but hey, either way, we're going to have some fun, huh? Okay. So, like I said, I got my notes here if you see me looking down. The failure of the V1 was really the most spectacular one I've had so far. All of the others split open, but they didn't just blow apart pretty much like this one did. I'm picking up pieces of rawhide 30 feet away. But before I really get into what I wanted to talk about, I wanted to kind of point something out about the reality of firearms in the 1400s. The fact is that firearms blew up a lot, and cannons and handguns. It was a problem. In fact, most of the handguns from the period that we find and are on museums and display across Europe were actually found in the moats of castles, and the breaches have split open. So it either blew up while the guy was shooting down at him, and it may have knocked him back and killed him, or it just blew up and was, useless after that, and he just threw it over the side and ran and got a crossbow or something. But it was a real problem, and the reasons they were facing this serious problem is really demonstrated in the Magna Gonne V1. Okay, first I want to address the gunpowder that I used. Now, the gunpowder itself was authentic medieval gunpowder for that time period. That is serpentine powder, uncompressed, uncorned, unscreened. It was made by dry grinding the materials individually in a ball mill for 24 hours each to a really fine talcum powder-like consistency, and then mixing them together by hand. And that's how they did it then. And the formula that I used was also the correct period formula. It was 60% by weight potassium nitrate, 20% charcoal, and 20% sulfur. And you might have noticed there's less potassium nitrate and more charcoal. So there's less oxidation going on, but more fuel. So it actually burned a little more slowly and a little dirtier because it was very inefficient. But by burning more slowly, it also produced lower chamber pressures. So because of that, the charge that I used was also period correct for the caliber of the gun and the type of projectile. I guess my serpentine powder is just better than what they were making then. Serpentine powder, being uncompressed, takes up a lot more volume than compressed powder. Now, in fact, I'm going to show this in a video coming up in a couple of weeks here. If you were to take a compression mold for black powder and you put about 1 inch of powder in it, then you put it in a 20-ton press and you compress that down, you can compress that 1 inch of serpentine down to about 1/4 of an inch. You can compress it down like 3 times. So, I mean, a gram is a gram, an ounce is an ounce, grain is a grain. That doesn't matter. It's just that the serpentine takes up a lot more space in the barrel than compressed corn powder does. So while it seems like that was a way too much powder to be putting in that barrel, yeah, it would be if it was like, say, a double F GoX. I'm surprised anything on the gun would have disappeared. But by weight, it was the correct charge. And really, that powder worked so well that I kind of think by itself it debunks this notion we have today about how underpowered and inefficient serpentine powder was back in the day. Now, the guns themselves were underpowered, but there were some reasons for that. It was more structural reasons of the guns themselves. We tend to want to blame it on the powder. Serpentine powder was less powerful, and still is, than corned powder, and corned black powder is less powerful than smokeless powder. But I don't think it was the powder that was really causing the problem. The amount of damage imparted to a target on impact by a projectile is called foot-pounds of energy. And foot-pounds of energy can be calculated with the following formula. That is FPE, foot-pounds of energy, equals the velocity of the projectile squared times its weight divided by a constant 450240. Now the constant is, I don't really know what the constant's for, but it makes the whole thing work. It's kind of like Einstein's speed of light squared is the constant that makes E equals mc squared work. Now, of course, the medieval engineers didn't have that formula, but where I'm going, I think they had kind of an instinctive understanding of this, because here's what all that boils down to. If you throw a baseball faster at somebody, it's going to hurt more when it hits them. Now, yeah, that is a great big duh, but the formula allows us to calculate and quantify how much more it's going to hurt. And we can manipulate the values of velocity and bullet weight, projectile weight, in order to match the two together, to get the right weight, the right powder charge, the right barreling, to get the FPE that you want. And then you can even calculate what you're going to get before you go out on the range and try it, which they did not have the advantage of back in 1400. But here's the problem they were facing. Their guns were blowing up. And they weren't blowing up at the muzzle. They weren't blowing up in the middle of the barrel. They were blowing up at the breech. They had a serious problem with handguns that cannons didn't really deal with so much. And the reason is that cannons were open. They were just open tubes, and they were breech loaded. They had a removable breech that they would put, a little tube that they would put the powder and the ball in. They'd shove that in the back of the tube of the barrel, put it over, stick a wedge in behind it so it's locked into place, and then they would shoot it. And you would just remove the wedge, pull the breech out, put in another breech. Well, you can't really do that with something the size of a handgun. Now, you probably could. I mean, especially with today's machinery and engineering skills and tools, we could make one, but obviously they couldn't make one back in the 1400s because there aren't any. And the solution of the removable breech plug worked with cannons. It certainly would have worked with handguns if they could have made them. The only thing they could do was they could cast their handguns out of bronze, brass, or iron so that it had a cast breech plug. But even then, they had an extremely high failure rate. Now, I don't know what that failure rate was, but I wouldn't be surprised if it was 50, 60%. Pretty much all the handguns we find from that period are failed. They've split open at the breech. So casting wasn't the answer. So they came up with the Hakenbüche. Now, the Hakenbüche had a fixed metallic breech plug that they fit into the back of the barrel, but they relied on friction to hold it in place. They'd heat the barrel up, they'd push the breech plug in, then when the barrel cooled, it would shrink, and they hoped that would hold it in place. But I can imagine that it had a pretty high failure rate too, because they recessed the barrel down into the wood and they put that breech plug up against a piece of wood of the stock. And I think the reason was they were hoping that if that breech plug did blow out, maybe it wouldn't blow back into the shooter's face and bury itself in his brain pan. Maybe that wood would stop it. Okay, so the engineers could not increase the lethality of their firearms by simply increasing the velocity. They pretty much had gone as far as they could with the structural integrity of the materials and tools and technology and knowledge that they had at that time. So you can't increase the velocity, but they could increase the weight. Which would you rather be hit with? A solid iron wrecking ball swinging towards you at 100 feet per second, or a BB flying at 300 feet per second. Well, hey, the BB's got 3 times the velocity, right? So if velocity beats mass, there's another one. An elephant stepping on your head at a velocity of 1 foot per second is going to do a lot more damage to your beanie than a BB hitting you in the head at 300 feet per second, even though that BB's got 300 times the velocity. Also, the caliber of Magna Gonne V1, 100 caliber, is also not too big for the period. In fact, most handguns were of a very large caliber compared to the later period. Now, think about back in the 1700s. Typical Brown Bess, depending on the time period and the model, the caliber of a Brown Bess would range from between 75 and 80 caliber. 80 caliber is pretty big, but there were some 80 caliber fowling pieces made back then too. Most handguns from the medieval period were a large caliber. They were 80 to 100 caliber. In fact, I've seen some that look more like hand mortars than handguns. And there's a very good reason for that. So the medieval engineers understood that they could reduce the velocity a little and increase the mass and still get the same amount of energy on impact. Even if you reduce the caliber, it doesn't make a big difference. I know it seems kind of counterintuitive, but somebody suggested I should reduce that caliber from 100 caliber to 50 or maybe even down to 40. I could go down to 36. I could go down to 31. It wouldn't make that much difference because lighter projectiles require more muzzle velocity to hit with the same foot-pounds of energy, and that means more gunpowder. And then the barrel explodes. It's not a linear relationship. It isn't like if you've got X charge of powder and you cut the ball in half, you get twice the velocity. You get a slight increase in velocity, but you have less mass now, so you really got to put more energy into it, not the same energy that you would put into a heavier. So you can't put the same energy into a lighter projectile and get more impact. So you still have to increase the powder charge even with a smaller caliber, and that was what they couldn't do. Now, yes, I could have made a handgun that had a 50 caliber barrel or 44 or even a 31, and I could have put a really low charge in it, and I could have built something that went pop and blew a little smoke out and maybe punched a hole in a 2-liter soda bottle and would have looked really pretty on YouTube. That's not what I need. I need a gun, okay? I need something I can take up onto the wall of my village, and I can take out 2, maybe 3 people charging up at the village with one shot. And that ain't going to happen with a little girly man 44 caliber handgun, okay? So my point is that 100 caliber back in the day would not have raised an eyebrow, to put it that way. So getting to the failure. If we look at where the failure occurred on Magna Gonne V1, we can see how it failed, and that'll tell us why it failed. Let me get it. Now, if you look here, this is the bore liner. This is a 1/8 inch. I'm calling it an iron pipe, but it's actually mild steel. It's the closest we're going to get to iron these days. There is no iron. You'll hear pipe called iron. Oh, black iron pipe. No, it's mild steel. Wrought iron. No, it's mild steel. There are different grades of mild steel, and they're down at the low end, but they still have more carbon than real iron had, especially back in the old days. The only way you're going to get real iron today is to buy it from a bloomery foundry. And there might be a few of those making hobby iron, here and there around the world, but you're not going to walk into a local Lowe's or Home Depot or go on Amazon and buy real iron. You're going to buy mild steel that they're calling iron. And that's what this is. This is the lowest grade of mild steel I could find. Now, notice it's perfectly intact. It's not split open out into a big, banana shape. Neither is the muzzle. The muzzle's perfectly fine. The barrel's perfectly fine. This might be flared out a little bit, but you can't tell by looking. I have to put some calipers on it. There's nothing obvious to be, flared out about it. But look out behind it, right behind it, all the way down. That's where it failed. It failed back here. This barrel or bore liner was just pushed down the bore and then butted up against wood here. And then in order to reinforce it, I wrapped 3 layers of rawhide from about here back to here. I know you saw the rawhide wrapping went back to here, but the touch hole wasn't back here, it was up here. The powder chamber was inside the barrel, so the maximum amount of pressure exerted in all directions on this was coming is inside that barrel or that bore liner, and it's fine. Structurally, from here forward was fine. But what happened is, as that powder burned, the expanding gas is pushing outward equally in all directions. That means it pushed back into the wood with as much force as it was pushing those bullets or projectiles out the bore, and the structural integrity of the wood simply could not handle that stress, and it failed and split open. The reason this gun failed was it does not have a fixed metallic breech plug. Now again, you might think that's kind of a duh category, but you'd be looking at it from modern eyes. Back in the 1400s, the breech plug was an overriding problem. It's why pretty much all of their handguns failed. It's easy to say, oh, just put a breech plug in it. Every gun since the early 1500s right up into the mid, maybe late 1800s, all had fixed threaded breech plugs. The problem in 1400 is tap and die technology will not be invented for another 100 years. So that ain't going to happen. I'm not going to thread a breech plug for it. And if I did, I'd have to double the thickness of the barrel in order to cut the threads in it and maintain any kind of structural integrity on it, which is a good idea anyway. It's 1/8 inch thick. 1/4 inch would be a lot better. And most blacksmiths could work with that thickness of steel anyway. So, yeah, you might be seeing some changes in Magna Gonne too. But, yeah, what are you going to plug it with? Well, I could get an iron, the 1-inch bore. I can make a 1-inch iron bar and slide up in there. Now, how do I hold it there? Well, I actually got several ideas about that. I'll be testing one of them coming up again with Magna Gonne V2. And I don't know that anybody in the 1400s used the technique that I'm going to be trying out, but they could have. My point is, with all of this testing, is nobody may have actually tried any of this, but they could have. There's nothing in any of this. There's nothing in the Magna Gonne V1 that even a small village blacksmith could not have made. Okay? People could have made these. They couldn't have drilled the bore out because they didn't have high carbon steel drill bits and electric drills. But what they would have done, I'll show you real quick. What they could have done and would have done is they would have cut the stock down about halfway down. Then they would have split the top half off, taken that off, then worked it out with a hammer and chisel to let the barrel lay down in it, put it back together, and then wrapped it with rawhide. They could have done that. I drilled it just to save some time, and it wouldn't have made any difference because that wasn't where the failure occurred. The failure was behind that. Okay, so thanks for watching my little presentation. I've actually stretched it out longer than I intended to already. Yeah, fixed metal breech plug. That is the only reason why Magna Gonne V1 failed. It had no fixed metal breech plug. And I think the takeaway from all this, and I'm going to put this down as the last of my wood handgun experiments. I doubt if I'm going to try any more of these in the future. The reason is, my opinion is, structurally wood simply is not strong enough to make up the bulk of a handgun. It's just not going to happen. Yeah, you got to have a metal lined bore. You got to have iron bands on it. You got to have a fixed metal breech plug. Oh, look, guess what you've got? You got a Hockenbush. You don't have a wood handgun. I think any attempts to make a wood handgun with as absolutely little metal, if any at all, possible in it, big enough and powerful enough to actually kill an attacker with, or 2 or 3, from on top of a wall down at the attackers. I just think that's not going to happen. The pretty little YouTube fake gun videos, yeah, you can do that all day. But a real, genuine, effective self-defense gun, no. And that's why you don't see any. There are wood cannons in museums, but there are no wood handguns. I think because they all blew up, people realized very quickly, this ain't going to work. And they trashed the idea and they went on to metal. So this is the end of my wood handgun series. Total failure, will not work. Even wood cannons did not have the problems that handguns had. As it turns out, as I've said, as it turns out, it's actually easier to make a functioning wooden cannon with a little metal in it than it is to make a functioning handgun with a little metal in it. You just don't scale these things up and down in a 1-to-1 ratio. And once we start scaling down, the structural forces just overcome the strength of the structural integrity, and down it goes. It just blows up. So, Magna Gonne V2 is coming up. I hope this answered a few questions, maybe gave an explanation or two. Hope I didn't bore you too much with it. And thanks for watching, and see you next time.